So 4.3 starts to talk about the definite integral. So the difference between this and what we're doing now is now we're finding the area under the curve. And we're doing that from a region from A to B. So here's what's going on. If we have a function, let's say this is our function f of x, and we're looking at from A to B, we're asking, what is the area under the curve for that piece of that graph? So sometimes it's going to be a nice geometric formula. So maybe it's a semicircle and we want to know the area under that semicircle. If we were to graph it, we would see that. Or maybe it's a rectangular region. So sometimes we can use a geometric formula. And then sometimes we have to use something called the fundamental theorem of calculus, which we will see in the next section. This section will focus on what the definite integral is, some theorems and definitions and properties of the definite integral, and then the geometric aspect. So when we talk about a couple of special definitions, let's say we have f that's defined at a, and we want to integrate from a to a. Notice that those limits of integration are the same. Since they're the same, then this area is going to be 0. So going back to our generic picture, let's say this is f of x, and we're integrating it from a to a, where here's a. That width, there's not really a width there because the beginning and the end point are the same. And since that width is 0, then it makes sense that this integral would have to be 0. And we could think about that almost like a rectangle. Thinking back to that last section, if the width is 0, then it makes sense that that would be 0. That second definition, if we have something that we could integrate, it's integrable between a and b, then if we switch those limits of integration, notice b's on the bottom here, and then a's on the top, then what will happen is it will change that sign of that integral. Theorem 4.6 is an additive property. Let's say we're integrating from a to b. If necessary, we could split that up between two integrals. So a good example may be something that looks like this. Maybe we have the absolute value here, and we're going from maybe -2 to 2. Remember, this is finding the area under the curve, and by that, I mean the area between the curve and the x-axis. So we don't have a formula for all of that together, but if you look at this guy's a triangle. It would be really easy to find the area of that triangle, and it would be really easy to find the area of this triangle. So then we could separate this and look at -2 to 0 for this function. This is the absolute value of x. And then we could look at 0 to 2. So this property just says if you can't integrate from a to b, or if you know something about part of that graph, then you could split this up into two pieces and then add them together. Theorem 4.7 are things that we actually saw a couple of sections ago. This just says we could pull that constant out and then integrate. And then this says we can split the definite integral up and integrate each of those pieces separately. So just same properties we saw before. The only difference now is that we have these limits of integration on that. A couple more theorems. Let's say we have a function that we can integrate and it's non-negative. Non-negative means that this thing lives above the x-axis. So then if that's true, then that area under the curve would have to be bigger than or equal to 0. So looking at something like this, let's say our function is f of x here, And we're integrating from A to B. We're looking at this piece. Because this f of x function is non-negative, that means that it lives above the x-axis, then we would expect this area to be positive. It would be 0 if our function was a line y equals 0 from A to B. Just because it would have, thinking about those rectangles again, it would have no height. So that leads us to talk about what happens if this function is below the x-axis. So if the function lives below the x-axis, maybe we have something that's doing something like this. From A to B. By area under the curve, we always mean the area between the x-axis and the function. So in this case, we would be talking about this piece. Because this function lives under the x-axis, then we would expect this area to come out being a negative number. And the negative just means it lives below the x-axis. And then 2, we have 2 functions that we could integrate over a closed curve. If f is below g of x, then we would expect that area to be smaller than the area under g of x. So let's look at an example. Suppose we have the function f of x here, and then we have another function that we're calling g of x, and we're looking at that piece from A to B. So if we look at that area under f, okay, notice f of x is less than g of x. Okay, that just means that that function lives under g of x. If you look at the area under f, we can see that that would definitely be smaller than that total area under g. Okay, so that's really all that part of that theorem is saying. So now let's talk about if we have a picture or a function, how would we write that definite integral? What would it look like? We're not talking about integrating it. We're just talking about how would we set it up. That's key and vital to what we're going to do in the next section. So here's our function. They're telling us it's 6 minus 3x. So that's what we're integrating. And we are integrating with respect to x. So if we look at those limits of integration, in this case, we're going from 0 to 2. So there's our setup. Looking at 19, we are integrating the function cosine of x. We're integrating with respect to x. That dx is important. We can integrate with respect to x or with respect to y. If we're integrating with respect to x, then we need those limits of integration to be with respect to x also. So those x bounds are from 0 to pi over 2. If we look at this one, we're integrating the function 25 minus x squared. And then thinking about those x bounds, we're going from negative 5 to 5. Okay, you may want to pause the video and try a few of these on your own and then check your answers to see how you did. So if we look at 18, our function is 4 over x squared plus 2. We are integrating with respect to x, and our x bounds go from negative 1 to 1. We always put the smallest one on the bottom and the biggest one on top. We're always reading that graph left to right. Now, I want you to notice this one's a little different. Notice that everything's going to the y-axis here, whereas these were going down to the x-axis. So that's going to change how we integrate this and the variable we're using. Also notice this is written in terms of y. So we have y cubed, oops. We're integrating with respect to y. So now our limits have to be with respect to y. So they're going from 0 to 2. If we look at this one, you have to think about how that function is written. That function is written as f of y equals. F of y is just a fancy way of saying x. So we would write our function as y minus 2 squared, or our equation. It's not necessarily a function. We're integrating with respect to y. And in this case, our y's go from 0 to 2. So now we're going to start talking about geometric formulas. So we're working a little backwards here. We have this function. We want to know what does that graph look like, and then can we figure out that area under the curve. So let's look at 23. We have the function y equals 4. That's coming from this. This is written in terms of x. So if it's a dx, it's always y equals whatever that function is. So here's our function, y equals 4. And we're looking at this from 0 to 3. Here's 0. Here's 3. So our picture would look like this. Now, this guy's a rectangle. And we can find the area of that rectangle by multiplying length times width. So our length is 3 and our width is 4. So that area would be 12. If we were to evaluate that, we would get 12. Okay, so once again, you may want to pause the video and see if you can try the next 3 and then check your answers when you're done. 25, we are looking at the function y equals x. And we're looking at it from 0 to 4. So we're talking about this piece. Okay, that is a triangle. So to find out the area of the triangle is 1/2 base times height. In this case, our base is 4. And then our height, if we were to plug a 4 in here, we're going to get a 4 out. This point is at the 0.44. So that's going to give us an 8. (29), we're looking at the function y equals 1 minus absolute value of x. So if you were to graph that, this is a transformation of the absolute value of x. Okay, so notice that it's flipped upside down and it's moved up 1 unit. So our graph would look like that. And we're integrating from -1 to 1, which happens to be this triangle. So once again, we're talking about a triangle. Area equals 1/2 base times height. In this case, our base is 2 units wide. And our height is 1. So we're going to get 1. And then 31. We're looking at negative 7 to 7. And the function y equals the square root of 49 minus x squared. Notice the y's are positive here. It's the positive square root. So if we were to square both sides and then move that x squared over, we end up with the equation of a circle. So this guy's a semicircle. It's the top half. And we have the radius as 7. So our graph looks like this. And since we are integrating from negative 7 to 7, we are looking at the entire half of the circle. Area of a circle is pi r squared, and we are looking at 1/2 of that, since it's just the top half of the circle. So we are going to get 49 over 2 pi as our area. If you wanted to write units, we don't really have anything specific, so we could just say unit squared on all these. Typically with integration, we don't include units unless there's some kind of application. So the last thing we need to talk about is using all those different properties to help us solve some problems. So let's look at a few of these. They're giving us some information about the x cubed function. They're telling us if we integrate from 2 to 6, we're going to get 320. If we integrate x from 2 to 6, we're going to get 16. And if we integrate just dx, and keep in mind this is understood to be a 1 dx, from 2 to 6, we get 4. So all these limits, notice they're all going from 2 to 6. And they want us to use those properties that we talked about before. So if we look at 33, what they've done is they have changed those limits of integration. So that's going to be equivalent if we were to take the negative and rewrite it from 2 to 6. So that's going to be negative 320. That's using one of those properties. I'm going to go back a few pages so you can see that property. It's using this property here. Okay, so if we flip those limits of integration, it does change the sign of our integral. If we look at 35, we're integrating from 2 to 6, but we have a 1/4 times x cubed dx. So we could pull that 1/4 out. I'm going to pull this down here. I need more room. So we have 1/4 going from 2 to 6 of x cubed dx. Now, we know what this is. They're telling us it's 320. We'll talk about how they got that in the next section. So 320 times 1/4 is 80. So that area would be 80. $37. They're integrating from 2 to 6. This is going to use that property where we can split it up, thinking about this is f of x and this is g of x. So we could rewrite this as 2 to 6 x dx minus 2 to 6 14 dx. So I'm going to keep that first one, but this 14 times dx, we could think about pulling that 14 out. and treating that dx as like a 1 dx. And we know the integral for that piece, and we know the integral evaluation for the other piece. So this ends up being 16 minus 4, which is 12. Let's think about that again. I forgot the 14. So this piece is 16 minus 14 times this piece, which is 4. So 16 minus 14 times 4 gives us a negative 40. So there's our answer. Now don't forget the multiplication that happens there. Let's look at the next one, 39. So we can split this up, integrate each piece separately. So we have the integral of 2x cubed dx minus the integral of 10x dx from 2 to 6 plus the integral of 7 dx from 2 to 6. And we're using that property that says we can pull the constants out. So I'm going to pull the 2 out of the first one, the 10 out of the second one, and then the 7 out of the last one. They told us this was the same thing as 320. This one is the same thing as 16. And this one is the same thing as 4. So when I substituted that in, I got 508 for 39. Let's take a look at the other ones. In 34, if we integrate, notice those integrands are the same. We're going from 2 to 2 for the limits of integration. If they're the same, then the area under the curve would be 0. 36, we could pull that negative 3 out. We know this from 2 to 6 of x dx is 16. And that's going to give us a negative 48. Let's look at 38. We are going to want to split that up. And then we could think about pulling the 6 out of the first one. And then pulling the 1/8 out of the second one. So you can see how we're using these properties over and over and over again. We know this guy is 16. And we know this one is 320. So I got 56. And then the last one. We're integrating from 2 to 6. We can split this up. pull the constants out, and then make your substitutions. Integrating x dx, we get 4. Integrating from 2 to the 6 of dx, we get 4. Integrating 2 to the 6 of x dx, we get 16. And integrating x cubed, we get 320. So I got negative 316 when I substituted that in. So then let's look at this last set. They're giving us a formula that we could find pieces geometrically. And we're going to use that to our advantage. Let's look at part A. I'm going to write over here. We're integrating from 0 to 2 of f of x dx. This guy could be described in terms of piecewise functions, but because everything's going to give us nice geometric formulas, like we have a triangle here, we have a semicircle here, and another triangle, then we can use geometry to help us find the area under the curve. Keep in mind, if it is above the x-axis, we're going to have a positive. If it's below the x-axis, then we're going to end up with a negative number. So we are integrating from 0 to 2 of f of x, which ends up being this piece. So this guy is a quarter of a circle. We know area of a circle is pi r squared. We want 1/4 of that. And because it's below the x-axis, we're going to get a negative number. The radius for this circle is 2. So if we multiply everything out, negative 1/4 times 4 would be 1, or negative 1. And then times pi would be a negative pi. So that area would be negative pi. B is asking us what's the integral from 2 to 6. What's that area for this function? So if we're looking at from 2 to 6, we are now talking about this piece. So let's think, what kind of formula can we use to find the area for that? In this case, we're talking about a triangle. The area of a triangle is 1/2 base times height. Our base is 4, and our height is 2. So our final answer would be 4. So now let's look at C. C is asking us to find the area between negative 4 and 2. So negative 4 to 2 would be this triangle, and it would be this semicircle. So let's find the area of that triangle. The area of a triangle is 1/2 base times height. The area of a semicircle is 1/2 pi r squared. Keep in mind, because both of these are below the x-axis, we will have negatives here. Our base is 2 and our height is 1. Our radius for that circle is 2. If we multiply here, we get negative 1. If we multiply out here, we get a minus 2 pi. So there's our area under the curve. And remember, by under the curve, we mean between the curve and the x-axis. So then D is asking us, what's that area between -4 and 6? So -4 is here. We're talking about all of this, including this triangle. So we have this piece. Now we just have to add on that piece. So in D, it's going to be a triangle plus a semicircle, which we already have all that, -1 minus 2 pi, plus another triangle. So that triangle, that last one, notice it's above the x-axis, so it's positive. 1/2 base times height. That base is 4 units long and the height is 2. So we're going to have 3 minus 2 pi for that answer.